This video is going to cover section 2.5, zeros of polynomials, and it's going to cover targets 2.8 and 2.9, listing all the roots of a polynomial given its equation or graph, and sketching the graph of a polynomial given its equation, and then writing the equation given its roots. Writing a polynomial equation with given zeros. Zeros are also roots or x-intercepts. So the very first thing that you want to do is to write the polynomial as a product of its factors. Quadratics that do not hit the x-axis have two imaginary roots. These take on a little bit of a different form. So if you have an imaginary root that's of the form plus or minus bi, so like 2i, then its factors are going to be x plus 2i and x minus 2i, but then you need to get them so that there's no longer an I in them. When you multiply them together, you just get x squared plus b squared. The other form is if you have a plus or minus bi, it factors into something a little bit different. It factors into x squared plus dx plus e, and this is where 2a equals negative d and a squared plus b squared equals e. We'll talk more about that in an example coming up. So after you've written the polynomial as a product of its factors, you'll want to place an a out in front of the factors, and this is the stretch factor. The third step would be to FOIL or box the factors until the polynomial is in standard form. The fourth step is to solve for the stretch factor. And the last step is to write the polynomial in standard form with its stretch factor found in step 4. So I'm going to walk you through these steps with a couple of examples. The first example is to write a 4th degree polynomial that has roots at 2, negative 2, and I, and such that it goes through the point 3, negative 150. Now one thing, if you remember, is that the degree of the polynomial tells you how many roots there are, and I only listed 3, 2, negative 2, and I, but you'll notice that complex roots always come with its conjugate, so if I is a root, then negative I is also a root. For example, if I had given you 3 plus 4i as a root, then 3 minus 4i is also a root. So knowing that these are roots, I'm going to start by writing the product of factors. So I have f of x equals, since 2 is a root, x minus 2 is a factor, negative 2 is a root, so x plus 2 is a factor, I is a root, so x minus I, and then since it's conjugate, negative I is also a root, you have to have the x plus I. Then if you multiply these through, so I did box with x minus 2 and x plus 2, and I get x squared minus 4. If you box x minus I and x plus I, you'll get x squared plus 1. And then don't forget to put that stretch factor out front. Then do box again with what you have, and you'll get x to the 4th minus 3x squared minus 4. And now is the time to plug in the point that it goes through. So you know it goes through 3, negative 150. So I'm going to plug in negative 150 for y and 3 for x to solve for that stretch factor. And you'll get a stretch factor of negative 3. And so then we'll plug the negative 3 back in to the polynomial equation and then distribute. And so our final equation is f of x equals negative 3x to the 4th plus 9x squared plus 12. Our second example is to write a 3rd degree polynomial that has 6 and negative 5 plus 2i as zeros. Zeros are also known as roots. And that it also goes through the point f of 2 and at negative 848. So remember that if negative 5 plus 2i is a root, then negative 5 minus 2i is also going to be a root. So now we have to do something a little bit different to find that factor. So we're going to use this x squared plus dx plus e, where 2a equals a negative d and a squared plus b squared is e, to write the factor of negative 5 plus and minus 2i. So negative 5 is a, and 2 is b in this case. So if negative 5 is a, 2 times a is the opposite of d, so we'll get negative 10 equals a negative d, and then that means 10 is d. And then over to the right here, plug in negative 5 for a and 2 for b, and you'll get negative 5 squared plus 2 squared equals e. Add those together and you'll get 29. And so the factor for this one is going to be x squared plus 10x plus 29. And then since 6 was a root, x minus 6 is a factor. And so here's the product of factored form. And then put the stretch factor out in front. And then the next step is to FOIL or box this through so that we can have one standard polynomial. So I'm going to do a box since it's a little lengthy than what you guys are used to. So up across the top I've got the x squared plus 10x plus 29, and along the side I have x minus 6. So if you do the box you'll get x cubed, and then you'll add these two combined like terms, and I get x cubed plus 4x squared minus 31x minus 174. And then now I can plug in the point that I was given. So I was given 2, negative 848. When I plug in 2, I'm going to get an a value of 4. So plug that back in to the equation and then distribute the 4. And this is my third degree polynomial that has roots at 6, negative 5 plus 2i, and negative 5 minus 2i, and it goes through the point 2, negative 848. Sketching a graph of a polynomial given its equations and a root or 0. These are going to be very similar steps to what we saw before, but now you're actually given one of the x-intercepts, and now you have to incorporate some synthetic division to find the other roots. So the very first one, just like always, is to determine the end behavior of the polynomial. So check out the degree, check out the leading coefficient to determine where it's rising and where it's falling. The second step is to use the given root and synthetic division to write the polynomial as a product of its factors. Step 3 is to plot the x-intercepts or roots, and one thing you won't be able to do is to plot any imaginary roots. They do not exist in the xy plane, so you'll only be able to graph or plot the real x-intercepts. And then also note the multiplicity of each root. So remember, if a root has odd multiplicity, it crosses the x-axis. If it has even multiplicity, it bounces off the x-axis. And then the last two steps, step 4, is to plot the y-intercept, usually that you can easily see in the standard form of the polynomial, or plot any other points that you know. So you can just plug in an x value and then find the y value. I will also give you another point, maybe the relative maximum or relative minimum, so you know how high or how low the graph bounces up or down. And then the last one is just to plot all those points and sketch the polynomial. So our first example is to sketch the graph of f of x equals x cubed minus 5x squared plus 3x plus 9, knowing that 3 is a root. Now you'll notice this isn't factorable, so I'm going to use synthetic division to find the other factors. So first of all, the end behavior. It's an odd degree and it's a positive leading coefficient, so that means it's going to fall left and rise right. Next is the synthetic division that I mentioned before. Oops. So remember, you're going to put the root is going to go in this backwards L, and then you're going to put the coefficients all the way across that. Always bring down the first number. So I'm going to bring down the 1. The 1's going to be multiplied with the 3. Put the 3 underneath the negative 5. Add those two together to get negative 2. Negative 2 and 3 is negative 6. 3 plus a negative 6 is negative 3. Negative 3 times 3 is a negative 9, and you'll get a remainder of 0. If a number is truly an x-intercept, your remainder should always be 0. If I tell you it's a root and you don't get a remainder of 0, then you might want to double check the math in your synthetic division. So now that I've done the synthetic division, 3 is a root, so x minus 3 is a factor, and then what my quotient is the other factor. So this is my x squared, because remember it drops down a degree. So I have x squared minus 2x minus 3. This can be factored further because I need to see what the roots are, and it factors to x minus 3 and x plus 1. And then just to rewrite this so I know its multiplicity is f of x equals x minus 3 squared times x plus 1. And so now I can easily see my x-intercepts, its multiplicity, and I already know my end behavior from the very first step. So on the next slide, I plotted my points at 3 and negative 1. Those are my x-intercepts. And then I also plotted my y-intercept. On the very first equation I gave you, the last number, the constant, is the y-intercept, and that's just going to help me a little bit with the shape of the graph. And I know it's going up to the right and down to the left, so I'm going to use my marker here. And then I have to remember it's going to bounce at a positive 3 because that has a multiplicity of 2. So it's going to cross. Oh. come down, bounce, and then go up again. Okay, so I apologize for the look of this. It's not easy to do with the mouse pad. So it crosses the x-axis at -1, it goes up through the y-intercept, comes back down, bounces, and goes back up. Right now, don't worry about where these other points are. As long as you have a y-intercept, don't worry about how high it goes. As long as you have the correct end behavior and the correct crossing of the x-axis and bouncing. So here is example 2 of sketching a graph knowing that 2 is a root. And unfortunately, time is running out, so I am going to let you guys try this example on your own, and we will cover it in class on Friday. The next part I want to show you is the assignment. It's page 322, and it's assignment 14. I'll be checking it sometime next week.